Greetings of this session. In this session, we will concentrate on Module 4, Laplace transformation and application. So this is the first session on Laplace transformation and its application. So in this session, we will study what do you mean by Laplace transformation, why Laplace transformation is required, and Laplace transformation of some basic function. So first, why Laplace transformation is required? So first question, before going through what is Laplace transform, why Laplace transformation is required. Now let us consider a circuit, very simple circuit I will consider, with R, L and C connected across a supply voltage V. R, L and C. As we know, this is the AC circuit. So this V is a function of time. So it is the varying function voltage. It is not a constant, not like a DC voltage. This is the varying input V of t. And if I need to find what is I, that is I of t, which is a function of time. Now normally to get the expression, what we will do, we will apply KVL. So by applying KVL, we will get V of t equal to R I of t plus L di by dt, L I of t by L di of t by dt plus 1 by C integration of I of t dt. Now this equation which defines the system is integro differential form. Integro differential form, right? So this equation, system equation, is in the form of integro differential form. Now from this form, integro differential equation, how to get the expression of I of t? Now there are various methods to find the solution, expression for I of t in a time domain analysis. Those are called as numerical methods. Numerical methods. It may be RK method, Runge-Kutta method, Euler's modified method, modified Euler's method, Milne's prediction correction method, and so on. There are many numerical methods exist to find the solution I of t for a given integro differential equation. Whereas all these numerical methods are iterative in nature. Iterative, what I mean? Iterative. You will not get the expression I of t directly, step by step. With the iterative techniques you need to find. So what is the drawback? Time consuming. Time consuming, lengthy. So iterative methods are lengthy and time consuming. So is there any other method to find I of t? Now these are the equation in a time domain. So if we transform the system equation into some other platform and manipulate in that particular platform, or transform into some other form and then manipulate manipulate means some operation to find I of t, then back, that is inverse transform. And bringing back from this transform platform to back to time domain transform. So this technique is easy compared to numerical methods. So there is a need of transformation. So from time domain platform we are transforming into some other domain, and then in that platform we are manipulating and then taking an inverse Laplace inverse transform, such that bringing back to original time domain. So this consumes a less time as well as this is easy. So how to transform? To what platform to transform? So there are various methods. One is Laplace transform, another one is Fourier transform, and Z transform, depends on a signal. So Laplace transform, Fourier transform, and Z transform. So in this module we will concentrate on only Laplace transform. Okay, so now for any given signal, given expression, we are converting into other platform. So to study the Laplace transform, till now we have analyzed why the transformation is required. Now what is a Laplace transform? So suppose a given function f of t, which is in a time domain, using a Laplace transform we are converting into f of s. This is the time domain, this is the s domain. So in the time domain, this is the t and this is f of t. Whereas f of s is represented in s plane, real of s, imaginary of s, or real of s is denoted by sigma and imaginary as j omega. So after transforming, the function in s domain changes, function in a time domain changes to function in s domain. So how to transform from time domain to s domain? There must be some transformation formula. So from the basics, if f of t is a time domain function, then Laplace transform of f of t. See here the notation L of f of t. This indicates Laplace transform of f of t equal to, denoted as capital F. So small case, lower case letters are denoted by for representing time domain function. Uppercase alphabet represents s domain function, Laplace transform, equal to 0 to infinity f of t e to the power minus st dt. So this is Laplace transformation formula. Laplace transform of f of t equal to f of s equal to integration from 0 to infinity f of t e to the power minus st dt. So now we will find Laplace transform of some signal. So before finding a Laplace transform of some functions, we'll study some standard function. Any signal is a combination of these standard function. So in the standard function, first one is step signal or unit step signal. Unit step signal is denoted by u of t. U of t equal to 1 for t greater than or equal to 0, 0 for t less than 0. That means x-axis is the t. For t greater than 0, this value is 1. So this is represented as u of t. So that means this signal is 0 up to 0, then it is changing to 1, and there onwards it is 1. Now then what happens? U of t minus t naught. U of t minus t naught is 1 for t minus t naught greater than or equal to 0. 0 for t minus t naught less than 0. T minus t naught greater than 0 means t greater than t naught. T greater than or equal to or t less than t naught. That means somewhere at t naught, this is u of t minus t naught. This is called as a shifted signal. The signal is shifted to right. Similarly, u of t plus t naught equal to 1 for t plus t naught greater than or equal to 0 or t greater than or equal to t greater than or equal to minus t naught, minus t naught, and 0 for t plus t naught less than 0, that means t less than minus t naught. That means it is shifted to left, minus t naught. So t greater than minus t naught, it is a 1, t less than minus t naught, it is a 0. Similarly, u of minus t. So u of minus t is 1 for minus t greater than 0 or t less than 0. One for minus t greater than or equal to 0 or t less than or equal to 0. For minus t less than 0 or t greater than 0. That means this u of minus t is a reflection of u of minus t is a reflection of u of t. Right? This is the t greater than 0, it is a 1. This is t less than 0, it is a 1. So it is a reflection. Now this is about a step signal. Now second category, impulse signal, impulse function or impulse signal. It is okay. Once again, we will consider unit impulse function, and it is denoted by delta of t. This delta of t equal to 1 for t equal to 0, 0 elsewhere. That means t at t equal to 0, its value is 1. So this is delta of t. So similarly, delta of t minus t naught, t plus t naught, all these things you can analyze similar to the step function. In detail, we will study while applying this. The third one is ramp, unit ramp signal. Unit ramp function, and it is denoted by r of t. Now this r of t equal to t for t greater than or equal to 0, 0 for t less than 0. That means why I represented this 1, 1 means this is the straight line with the slope 1. This is the straight line with the slope 1. So that is why it is called as unit ramp function. Unit means slope 1. Slope is unity. So similarly, what happens? R of t minus t naught. I will not write the expression directly, I will plot. So this is t naught. So this signal is shifted from 0 to t naught. R of t plus t naught is shifted behind this. Right? Okay. Now we will see a Laplace transform of some basic function. Okay, so some basic function. So first one, as we have studied, Laplace transform of u of t. Now by the definition of the Laplace transform, so Laplace transform of u of t is equal to integration from 0 to infinity u of t e to the power minus st dt. Now by the properties of u of t in this interval 0 to infinity, it is 1. So if I substitute that, so it is 0 to infinity limit integration 1 into e to the power minus st dt. Now what is the integration of the e to the power minus st dt? e to the power minus st divided by minus s. Put the limit integration 0 to infinity. Now it is equal to e to the power minus infinity by minus in s minus e to the power minus 0 by minus s. Now e to the power minus infinity means it is a 0. So this entire term becomes a 0. E to the power minus 0, it is 1 minus of minus, so it is 1 by s. So Laplace transform of u of t equal to 1 by s. Second, as we have seen some basic signals, now we will find Laplace transform of some basic function, Laplace transform of delta of t. Now according to the basic principle or formula, it is 0 to infinity delta of t e to the power minus st dt. Now this delta of t is 1 only when t equal to 0. For all other cases, all other intervals 0 to infinity, 0.001 to infinity, it is 0. So entire thing becomes 0. So when delta of t is equal to 1, that is at t equal to 0. So it is e to the power minus st at t equal to 0. Not an integration, at t equal to 0. So at t equal to 0, it is e to the power minus 0 equal to 1. So Laplace transform of delta of t equal to 1. Third one, Laplace transform of r of t. R of t is the same as Laplace transform of t. Okay, that is by definition 0 to infinity r of t e to the power minus st dt. So in this interval 0 to infinity r of t equal to t, so it is 0 to infinity t e to the power minus st dt. Now this integration with respect to time, and this is product rule, t e to the power minus st. So based on the product rule, integration of products, it becomes t e to the power minus st by minus s minus integration, okay, this I'll put 0 to infinity, then integration 0 to infinity e to the power minus st by minus s into 1 dt. Based on the product rule, integration of uv is equal to u integration of v minus integration of du integration of v. So based on that, t e to the power minus st by s 0 to infinity minus integration 0 to infinity, integration of e to the power minus st is e to the power minus st by s, differentiation of t is 1 dt. Now this case, when t is equal to infinity, this term is 0, and lower interval, lower limit t equal to 0, this is 0. So entire thing becomes 0, minus into minus plus 1 by s integration 0 to infinity e to the power minus st dt. So it is 1 by s integration of e to the power minus st is e to the power minus st by minus s 0 to infinity. That means 1 by s e to the power minus infinity by minus s minus e to the power minus 0 by minus s. Once again this becomes 0. Minus into minus plus e to the power of minus 0 is 1. So 1 by s into 1 by s. So it is 1 by s square. So Laplace transform of u of t is 1 by s. Laplace transform of delta of t is 1. Laplace transform of r of t or t equal to 1 by s square. Few more. Now Laplace transform of constant k. Some constant, Laplace transform of some constant k equal to, according to the definition, 0 to infinity k into e to the power minus st dt. That means k is constant 0 to infinity e to the power minus st dt, and limit integration of e to the power minus st dt in the interval 0 to infinity is 1 by s. So it is k by s. So Laplace transform of k is k by s. Okay. Now Laplace transform of exponential decaying function. Laplace transform of e to the power minus et. Now according to the definition, 0 to infinity e to the power minus at e to the power minus st dt. So e to the power a into e to the power b is equal to e to the power a plus b. So this is 0 to infinity e to the power minus s plus a into t dt. So it becomes e to the power minus s plus a into t, because integration with respect to time is e to the power minus s minus s plus a in the interval 0 to infinity. That means e to the power minus infinity when t is equal to infinity minus s plus a minus e to the power minus 0 by minus s plus a. As we know, e to the power minus infinity is 0. So this term becomes 0. Minus of minus is plus, and e to the power minus 0 is equal to 1. So it is equal to 1 by s plus a. So Laplace transform of e to the power minus at is equal to 1 by s plus a. Now Laplace transform of t to the power n. Laplace transform of t to the power n, by the definition, it is 0 to infinity t to the power n e to the power minus st dt. Now this is also function of time, this is also function of time. So integration of products. So in this case what will happen? So it is t to the power n e to the power minus st by minus s, product rule 0 to infinity minus integration 0 to infinity e to the power minus st by minus s t to the power n differentiation n t to the power n minus 1 dt. E to the power integration of e to the power minus st is e to the power minus st by minus s. Integration of differentiation of t to the power n is n t to the power n minus 1 dt. Once again this is the product rule. Okay. Now what happens to this? When t is equal to infinity, this is 0. When t equal to 0, this is 0. So this entire term becomes 0. So it becomes minus into minus plus, n is a constant with respect to t, s is a constant with respect to t. So it becomes n by s integration 0 to infinity t to the power n minus 1 e to the power minus st dt. Now this and this is similar. Instead of t to the power n, it is t to the power n minus 1 e to the power minus st dt. So what will happen? Then it becomes n by s into n minus 1 by s. So continuously it will repeat such a way that n by s, next time this integration will become n minus 1 by s, then this becomes n minus 2. So next n minus 2 by s continuously up to 1 by s integration 0 to infinity e to the power minus st dt. Correct? When this n minus 1, n becomes 0. Right? So after successive increment, this n minus term becomes 0, t to the power 0 becomes 1. So now this is n into n minus 1 into n minus 2 up to 1 divided by s to the power n. Now what is the e to the power minus st integration? E to the power minus st by minus s 0 to infinity. This we have already calculated and it is equal to 1 by s. Now what is this? N into n minus 1, n minus 2. It is same as n factorial divided by s to the power n. Once again s. So it is s to the power n plus 1, which is equal to n factorial divided by s to the power n plus 1. So Laplace transform of t to the power n is equal to n factorial divided by s to the power n plus 1. Next, Laplace transform of sin omega t. So Laplace transform of sin omega t cannot be calculated directly. So I'll write this sin omega t function as Laplace transform of e to the power j omega t minus e to the power minus j omega t by 2j. So we know that sin omega t is equal to e to the power j omega t minus e to the power minus j omega t by 2j. Now this is a constant. So 1 by 2j into Laplace transform of e to the power j omega t minus e to the power minus j omega t. So what happens is 1 by 2j, it is Laplace transform of e to the power j omega t minus Laplace transform of e to the power minus j omega t. Now we know the Laplace transform of e to the power et. So this is 1 by s minus j omega minus 1 by s plus j omega. Because Laplace transform of e to the power minus at is equal to 1 by s plus a. So e to the power j omega t becomes 1 by s minus j omega. Now simplify. So 1 by 2j s minus j omega into s plus j omega LCM equal to s plus j omega minus s minus j omega. So here s gets cancelled, j omega plus j omega. So 2j omega divided by 2j into what happens is a minus b, a plus b, a square minus b square, where j is j square, so j square is equal to minus 1 s square plus omega square. So this is equal to omega by s square plus omega square. So Laplace transform of sin omega t is equal to omega by s square plus omega square. So if we find Laplace transform of cos omega t, so similar to sin, we will rewrite in terms of e to the power j omega t plus e to the power minus j omega t by 2. This is the exponential form of the cos omega t. So it is 1 by 2 into Laplace transform of e to the power j omega t plus e to the power minus j omega t. Similar to sin omega t, it is 1 by 2 omega divided by s minus j omega plus 1 by s plus j omega. So while doing so, 1 by 2 s minus j omega into s plus j omega in the denominator, in the numerator s plus j omega plus s minus j omega. So j omega gets cancelled. So it is 2s by 2 into s square plus omega square. So it is s by s square plus omega square. So Laplace transform of cos omega t is s square plus s by s square plus omega square. So in this session we concentrated on what is the Laplace transform, basics of Laplace transform, and then some standard signals, and then Laplace transform of some basic functions. So we will solve some problems on this in the next session. Thank you.